Okay, so we are now going to properly go over this question. Actually, just on a preference, if you were at the end of the tutorial and you noticed that we got a negative x value, that didn't mean we did it wrong. It meant that the numbers I gave for the question, which I made up myself, were wrong, and the ladder was already in equilibrium. So the only way for it to be in limiting equilibrium would be if you removed mass. But that's not particularly important. What we're going to do is set up the system completely arbitrarily, and then solve the official problem, and hopefully we should have no problems. So to start with, we're going to put absolutely no numbers in, and we're just going to consider a system where the general type of question where we have a ladder, which is against two rough horizontal surfaces. I'm going to call this point B, this point A. Both of these things are rough. We say that the wall has some coefficient mu W, and the ground has some coefficient mu G. And we're told that a mass is placed somewhere, a distance x, along this wall, and that causes the system to be in equilibrium, and find what the value x is. So we're going to call the center of mass, we'll call this big M, and we'll call little m the extra mass which is added. And so the force acting down both get a factor of G. And then we must have a reaction force at the wall. And as mentioned, by assertion, we have a force which acts up at the wall. Again, against the direction of motion is the thing to remember. And then at the ground here, we have a reaction force acting upwards, and we have a force acting inwards, which we'll call Fg. And we're going to do this for an arbitrary angle, theta, to begin with. Okay, so how do we find x in a general sense? Well, before we may have to solve the actual values of f and r, but on a more sort of meta sense, what we're eventually going to do is take moments, and this thing is going to be in limiting equilibrium when the anti-clockwise and clockwise moments of this system are balanced. So we need to work out what are the anti-clockwise moments and the clockwise moments, which means specifically we need to work out the components of each of these forces along the perpendicular direction to the pivot. So they're forces along each of these lines. So how do we do that? Well, let's consider we have this define our parallel direction, and we have some arrow there, and we know that it acts at some angle theta, and we want to, sorry, we have an arrow acting directly downwards, so my apologies. And we want to find the component of the arrow which is acting in that direction, or equally, we could build the arrow from along the slope and against the slope, like so. Okay, using some simple geometry, because we know this angle here must be 90 minus theta to make this thing balanced. This thing must be equal to theta. So this direction along the thing here is cosine theta. So for these things, the direction along the slope is mg cos theta and little mg cos theta. So that's all good. And the same is going to hold true for this force Fw, right? Because it's in the same plane of force. So we could just flip the diagram into this direction, then we'd have a line of symmetry here. So we're going to also be considering that angle, which is also going to be cos theta. So we're going to have a force there, which is Fw cos theta. And then the reaction force at the wall is going to be slightly different. So let's consider that independently. So I've got it acting out this way. I know that to the ground, this makes an angle theta here. And I want to find the component of this, which is along the perpendicular direction. So this component of it, which interacts with this component of it to build the whole thing, that's right angle there. I know that this thing must be an angle theta. This thing is straight, so this must also be an angle theta. And so this component here must be the sine of theta. So I also specifically have RW sine theta acting. So they're my components. There's your geometry. to build those, but I encourage that to have a go at that yourself. Build those angles because geometry is really helpful through intuition. But this is now my diagram, which completely constrains all of my things. I have 4 moments acting, which will cause this thing to try and move. And if it's in limiting equilibrium, this means these things are bonus, which means that FW cos theta times, well, we'll say the whole thing has a length L. So L FW cos theta plus L RW sine theta must be equal to, and then this is acting at a halfway point because it's a center of mass, so L over 2. In fact, let me draw that on for the sanity of the whole diagram. It's getting a little bit scrappy. But this whole thing is a length L. So this is L over 2 mg cos theta, and this thing here is x times mg cos theta. So there we go. This now constrains the motion. So solving this for x is all that we are asked to do. But obviously we have a lot of variables in here so far, so we have to start eliminating them, which is the next part we'll come on to. But immediately, just in terms of this algebra, there's a bit of a step we can take because we know it's in limiting equilibrium against the wall's rough surface and the ground's rough surface. So we know in general we must have that Fw is equal to mu w rw and Fg, which we haven't used in this because we've taken A as the pivot, is equal to mu g rg. So we can immediately actually make a substitution here that L mu w rw cos theta plus L rw sine theta is equal to L over 2 mg cos theta plus x mg cos theta. Now, a very useful tip before we go on to solve what for RW actually is when we're getting to the stage, and you're getting to the stage in further maths now where you're having these long, brutish expressions. If we try to plug numbers in immediately, this is going to get very, very messy. So it's often a lot simpler to just stick to the symbols, the variables, the letters, rearrange your algebra there, and then plug in the numbers later. That's how it's best done. So we can factor out here L RW, and then I'm left with mu W cos theta plus sine theta. Then that's going to be take away L over 2 mg cos theta. And then if I put that one in brackets and divide the whole thing by little mg cos theta, that gives me x. And now I can just find well, once I'm given m, big M, and I find what RW is, and I put this in as well, I know what my answer for x is. So that is going to be the next thing that I will